So guys, this time I will be discussing to you some of the provisions on the unification on the determination of how ductility is achieved, no? Both in compression members like columns and flexural members like beams. So the first question we will be answering tonight is how to determine the net tensile strain in the extreme tension steel, considering the provisions of the ACI regarding compression control and tension control sections. So here we have a figure where the possibility of getting the um, net tensile strain of the extreme tension steel, which is actually at this level. Okay, so this is the extreme rebar or steel reinforcement in tension. So we are not concerned with the other layers since ductility is defined on the basis of the yielding of this extreme most tension steel. So this layer, no, of steel at the extreme tension side will dictate how ductility is achieved. So certain limitations in the code are defined in terms of strain limits upon which ductility is measured. And the first limit here defines what you call the compression control limit, while this point here defines the tension control limit. So in between these two limits is a gray area that allows you to either consider the behavior uh, in terms of flexure or in terms of compression. So the control of ductility in this region in between the tension controlled and the compression controlled region is actually manipulated in terms of the reduction factor. Okay, so we have the reduction factor phi that will dictate some concerns on ductility in the transitions. Okay. Okay, so let's go back to the main question on how we determine this. So we simply make use of a strain compatibility relation and make use of some geometrical uh, proportioning on the strains, as we all know that the epsilon cu according to ACI is actually 0.003. Okay, so the actual strain now is actually represented by this dotted or dashed line And this is the one that we need to compute and compare it with the limits. If it falls less than epsilon cc, then we can say that this is a compression control design. And if it falls beyond this limit, so this point here will give you a tension control design. Okay, so we actually change the description for a ductile and a brittle failure to a compression and tension control failure. That's why it's called a unified provision, because we are not we are looking into the behavior both on columns and beams. So we just don't restrict it with the beams, and we just don't restrict it with columns. Okay, so the procedure is a simple ratio and proportion that perhaps will be accompanied by the equilibrium condition. Okay, so if we take, okay, I'd like to jump over to this computation. Okay, so for a simple rectangular section, this is the start of the process in determining the net tensile strain. Okay, so we simply make use of an equilibrium equation equating tension and compression. Okay, upon which your location of the neutral axis, whether it's a tension control or a compression control, doesn't matter, can actually be defined on this basis. Okay, so if we know the area, so we can actually simplify this as area times Fy must be equal to 0.85 F prime C beta 1 C. Okay, so if we can solve for C here in terms of AS, we can easily solve for epsilon T as well. Okay, because simple triangular relation can be used. Okay, so we can simply make use of this figure to solve for C. If this is 0.003, then we can uh, determine the level, the net tensile strain may be at the center. Now, if it's a two-layered or a three-layered beam, then we first make use of an epsilon T. And then if you want to, okay, so this is at the center of gravity. So we convert this into an epsilon T at the extreme tension fiber, or sorry, at the extreme tension steel. Okay, so our target is only to solve first for C, and then we get epsilon T. Because if you know C, we can easily go back to our original figure here. Okay, if we know C here, we can simply go back to this figure and get this one by a simple relation. Okay, whatever uh, steel areas here, we can relate it later by transferring the center of gravity of the total stir area with that of the centroid of the extremmost tensile steel. So that's how to solve for the net tensile strain in the extreme tension steel. So this is needed to carry the next step because we need this epsilon T here to carry on the next step on determining your redistribution factors and of course your reduction factors as well. Okay, as well as your reduction factor. So that's it for now. I will be explaining to you the details of these ACI provisions on the next video. Thank you very much.